Welcome, ladies and gentlemen, to the second of our little review lectures. Remember, in these lectures, I'd like to review some topics we covered in the class this semester, but we're going to do it by taking a little bit of a more fun look at just some particular topics. And today, we're going to review just a couple of physical topics by looking at cars, okay? And today, I think, is going to be probably even a little bit shorter than the review one that we had with the cats, okay? So let's start this review by just looking at a car going through a banked curve, and I believe this was a homework problem at some point in the past, okay? So let's say we have a car going through a curve of uniform radius. So we have some curve here, and it could be a piece of a circle. It has a uniform radius r, okay? And then let's say the curve is banked at some angle theta, okay? And then we have a little car on it. Okay, it's a little bumper, shaped like that, I guess, or a top hat with pillars. I don't know what it is. That's a car, okay? And so the question is, how fast can it go through the curve without sliding? Okay, so the forces on the car are the normal force up. We have the force of static friction down, because remember the tires are going to roll without slipping, which is static friction. And then we have mg straight down. Okay? And the force of static friction, in this case, is pointing down because it doesn't need to keep the car from sliding down the ramp. It needs to help turn the car, right? Help turn the car around the corner. So it needs to point down the ramp. So then we want to pick a coordinate system, a nice coordinate system to use here. And the one that I'm going to pick is actually this one where x is horizontal and y is vertical. Now, normally when things were on ramps, we were aligning our coordinate system with the ramp. So the question is, why didn't I do that this time? Why do I think it's a better choice to use this flat coordinate system this time? And the reason that I didn't is because if we consider going around the curve here at constant velocity, this top picture, I'm going to have a centripetal acceleration, right? Which by definition is v squared over r. So this centripetal acceleration, it's going to point horizontal because the curve goes around in this shape, if this is looking at it from above, in the horizontal plane, right? So AC is going to point like this. And so when I find AC, instead of pointing the vectors along the ramp and finding components of AC, I'm just going to make my coordinate system in the beginning point so that one of the unit vectors points in the direction of AC, so that I can just find AC without having to find components of AC. Okay? Now the downside of this, making sure that it points in the direction of the centripetal acceleration, is I have two different forces that don't point along unit vectors, right? Usually we put it along the ramp because that means that gravity is the only thing that doesn't point in a unit vector direction. In this case, I have two that don't point in unit vector directions. So my picture looks like I have Fs at some angle and I have gravity straight down, right? And this Fs makes this angle with the horizontal line theta, right? Because it's the Fs is the same angle as the ramp. And so then if I extend this line this way, and I extend this line this way, then if I draw in a horizontal line here, and then I have the normal force like this, okay, and it extends down this way. So then what do I have here? Let me make this a little bigger just to give myself a little more room. So the force of static friction points in this direction, and then if I add in a horizontal line, this is theta. Okay? So this is 90, and we'll call this angle phi. Okay? And theta plus phi must equal 90 degrees, because it's a triangle, right? And 90 are used up for the right angle down here. So the other two angles must add up to 90 degrees. So that's phi. And then just by geometry, when I have two lines that cross like this angle that's kind of across from it is going to be the same angle, okay? With the vertical line on one side and this same line on the other, okay? And then this one is the angle of the ramp, right? And then this guy here is the normal force, and they make a 90-degree angle, right? But phi of that 90-degree angle is here, so then this must be theta of that 90-degree angle, because phi and theta add up to 90 degrees. But then this is vertical right here, and this is horizontal right here, so this must be phi again. But then again, this is the angle of the ramp down here, and this is the normal force, so those make a 90-degree angle, and phi of it is used up here, so this angle right here must be theta, okay? So then if I go back to my picture and draw a dotted line for this horizontal direction, this, by geometry, must be theta, okay? And that gives me a nice way to break down the normal force and the friction force into components, okay? It's theta here, it was phi, and then this one is also theta, okay? So then what are we going to do? We're going to use Newton's second law, right? And let's use it in the y-hat direction first. So y-hat is the normal force times cos theta, right? Minus mg. And then minus the component of the static friction force that's in our y direction, right? Which is Fs sine theta, okay? And that is going to equal 0 because in our y direction, the vertical direction, nothing's happening, right? The car's not going up and down. There's no acceleration in that direction, okay? And then that is equal to n cos theta minus mg minus mu sub s n sine theta, right? And that tells me that n, that equals 0, of course, that n equals mg over cos theta minus mu sub s sine theta. Okay? So n equals mg over cos theta minus mu sub s sine theta. So then we're going to do the same thing for the x-hat direction, right? And in the x-hat, we're going to have n sine theta, right? This little piece up here, plus fs cosine theta. Okay? But in this case, there is an acceleration, right? MAC. There's this centripetal acceleration pointed in this direction. Okay? So that tells us that n sine theta plus mu sub s n cos theta equals m and then v squared over r. Okay? That means we have n times sine theta plus mu sub s cos theta equals m v squared over r. And then I can plug in for n, right? So I have mg sine theta plus mu sub s cos theta. That's all over cos theta minus mu sub s sine theta. And that equals m v squared over r. And then the question is, what's the maximum velocity that the car can go through the corner without slipping, right? And so we see from this that pretty simply, v is going to equal g times r sine theta plus mu sub s cos theta over cos theta minus mu sub s sine theta. And that's all in a root. Okay? And so that tells us that, of course, the maximum speed that the car can go through the curve with is going to depend on how much it's banked, right? Remember, theta was just the angle that it was banked at, and what the radius of the curve is, right? So the tighter the curve is, the slower the car is going to have to go to not slide, right? And the more we bank it, the faster we can go without sliding, okay? Because more and more of the car's weight is pointed in this direction down the ramp, right? If we break it into components where it points normal to the ramp and along the ramp, this straight down is closer and closer to in the direction of the ramp as we make the ramp steeper, right? So that's the banked curve, and that's the reason that you don't see a lot of banked curves on normal driving roads, right? Because they don't want people to just go as fast as possible. But when you start to see racetracks and things like that, you start to see a lot more banked curves, because then the point is speed, right? And so then they bank the curves so that the cars can go even faster through the corners, okay? So now let's move on and let's consider car suspension, okay? And the suspension in your car is there to allow the car to absorb some of the jolt when it goes over a bump, right? And the suspension ultimately looks like a mass sitting on top of a spring. So the suspension we can kind of model as like this mass just sitting on top of a spring, right? And if we have a mass sitting on top of a spring here, it's going to, even at its resting point, right? Even when it's in equilibrium, there's no net force on it, it's still going to have squished the spring by some distance L, okay? And so when it's just sitting there and nothing's happening on it, I'm going to write Newton's second law, and I'm not going to incorporate any of the signs for direction, okay? So we just know that the force that the spring applies is minus kx, right? And x is L in this case. And then plus mg equals ma, right? And a, we just said it's in equilibrium, so a must be 0. Equilibrium means no net force, right? So that tells us that KL equals mg, right? But then if we consider the case where the spring gets squished a little bit more, so it would sit here, L down, and it gets squished a little more, distance x, then I can do the same thing. And again, I'm just going to use Newton's second law, and I'm not going to incorporate the signs for the directions of the forces. I'm just going to write the definition of the forces. So the spring is always going to do minus kx, and in this case, x is L plus x, right? You're going to have the force of gravity still acting on the block. And now it's going to equal ma. Because now there is going to be an acceleration, right? Now it's not in the equilibrium point. The equilibrium point was here, where the spring is just squished by L. Okay? And then remember, KL equals mg. So this first term in here is going to be minus KL, which is minus mg. So it's just going to cancel this term. And what I'm going to be left with is minus kx equals ma. And therefore, a equals minus k over m x. And this one, remember, this was the exact differential equation that we solved. Remember, this is a differential equation because a is actually d squared x dt squared. This is the exact differential equation that we solved when we had the mass. Let me draw it over here. When we had the mass on the spring sitting on the frictionless surface, right? It came out just like this. And so what we have here is something that's going to move in the exact same way that the mass sitting on the frictionless surface works, okay? And it all comes from the fact that the force applied by the spring is directly proportional to how much we squish the spring, okay? So then in the end, the weights cancel out because the spring is already squished by a certain amount that counteracts the weight of the object, okay? And so, with all that being said, since we ended up with the same differential equation, we know that we're going to end up with the same equation describing the position of this particle, right? X equals a cosine omega t plus phi, where omega equals k over m in a root. So we're modeling your car as just a mass sitting on top of a spring, right? But really it's a mass sitting on top of 4 springs. And the 4 springs would each have a K of something like 30,000 newtons per meter. Okay? And so we're just going to say that your car, the whole mass, right? So if we're doing the 4, we would take the mass and divide it by 4 and say, okay, so each spring holds up 1/4 of the car. All right? We'd approximate it like that. But if we're going to do the whole mass of the car, then the K for the springs is just going to be 4 times that. It's going to be 120,000 newtons per meter. And if we just have kind of a large, like a luxury sedan or a big muscle car or something like that, a normal mass is going to be like 2,000 kilograms. Okay? So then what's the natural frequency of this system? You can see if I just take these numbers, I'm going to get omega equals k over m in a root, and that's equal to about 7.7 radians per second. Okay? And that gives a frequency, because remember omega equals 2 pi f, that gives a frequency of about 1.3 hertz. And the best information I could find about this said that riders tend to consider the ride a little harsh if this frequency goes above 2 hertz. So you can see, if I had a car that I wanted to have a very stable body, I would make this K bigger. Okay, so when I have a car that's tuned to be like a race car or something, I make this K bigger. I make the suspension stiffer. And what happens is if I make K bigger, omega goes up, right? So this frequency, this natural frequency goes up. So I can describe the kind of stiffness of the suspension by the natural frequency that the suspension would have. And apparently, when this frequency is above about 2 hertz, people say that the ride feels harsh, okay? That it's a little too bumpy inside. And the problem with this whole thing is that simple harmonic motion never stops, right? This equation, I can just keep plugging in bigger and bigger t's out to infinity, and it's still always going to give me some value, right? The thing is always just going to keep bobbing forever. Now, with a real spring, it won't bob forever, but it could still bob for a long time. And we don't want that in a car, right? We don't want it so that every bump you go over adds a new bounce to the car that just like continues until you park the car, right? So what we want to do is we want to damp this motion so that the car doesn't bob up and down for a long time after every bump. So what car manufacturers do is add shock absorbers, okay? And what it is you can see the spring right here, right? That spring is the spring that we were just talking about. And then this thing, what are usually called the shocks or the shock absorbers, it's just a thing that's designed to create friction. So it creates a friction that opposes the motion, right? Friction always opposes motion. And it creates friction that just takes energy back out of the system so that the thing doesn't bob up and down for a long time. So for people who haven't like worked on their own car before or anything like that, this is going to be the inside of the underside of a car, where this stuff over here, this silver piece, this is the rim of the wheel, and this little bit of black right here and right here, that's the beginning of the tire, okay? This part right here is going to be your brakes, and then it sits on an axle, and attached to the axle is this big spring here that allows the car to not jostle the whole car when it goes over a bump, right? It allows the wheels to move without moving the body of the car very much. And then the shock absorber here that we just said takes energy out of the system so the car doesn't bob up and down forever after the wheels get bumped once. So when we damp a simple harmonic oscillator, we still have this equation for the motion, right? X equals A cosine omega t plus phi, but I'm going to call this omega prime because we'll get a different omega for a damped system. And we change this a, okay? So I'm going to call this a prime. Okay, so what are a prime and omega prime? A becomes a prime, which is equal to a, right? The initial. So we'll call this a naught, okay? And we'll take the prime back off because now we know that we're talking about the damped system. So we'll call this a initial. So you can imagine if I go over a big bump, I squish the spring by some amount, okay? That amount is this a. And there's not really any changing that, right? Damping it doesn't really change it very much because, yeah, it'll add a little bit of friction, a little bit of resistance to going up, but it's not enough to really noticeably change it. So this is just however much the spring gets squished when you go over a bump, okay? And then this e to the minus b over 2m t. Okay? And this, remember, just like we had when we did the cat thing and we had Usain Bolt, I even mentioned the damped oscillator, right, as an example of exponential decay. So here's our exponential decay. It's e to the minus something x, okay? So e to the minus some constant x is always exponential decay of x, okay? So if this is y and this is x, it always looks like this, okay? It's some kind of exponential decay like that. And in our case, the x is t, right, the time. And then a is the y, okay? And so this is going to have this effect. And then because it's on a cosine, it'll sometimes be negative, but you'll get this same squishing effect in the negative axis as well, okay? So the amplitude is going to get squished by this exponential decay function. And then omega prime is equal to k over m minus b squared over 4m squared in a root. And so you can see this is this k over m in a root. So this is omega squared minus b squared over 4m squared, right? This could also be expressed as omega, where this is the natural frequency, right, squared minus b squared over 4m squared. Okay, so what's b? B is a constant that describes the strength of the damping force, okay? And you can see from this or from this that B must have units. This little equals of 3 bars is usually units of, is how I've usually used it. And so this B must have units of kilogram per second, right? For this to work out, because the power of E here can't have units. And this thing here has to come out with these units, okay? So the units must be kilogram per second. And K, of course, is newtons per meter, right? Which is kilogram per second squared, okay? Okay, so B is some constant that describes the strength of the damping force. And then kind of a normal goal for damping in car suspension might be to have the amplitude of the oscillation gone in like 3/4 of a cycle, so that if you start by going over some big bump, it goes down and goes past equilibrium and rebounds, and then it comes up, and then it's done, okay? So this is 1. Let me see if I can find a way to show you guys this. This is 1, 2, and then 3 pieces of the cycle, okay? From top to equilibrium, that's 1/4 of a cycle. From equilibrium to the trough is 1/4, and then from trough back to equilibrium is 1/4. And this looks really uneven. It looks like it's not a quarter because of the exponential decay. But if you think of my kind of perfect cosine function, right, then from crest to equilibrium is 1/4. from equilibrium to trough is a quarter, right? So here to here is 1/4, here to here is 1/4, and then here back to equilibrium is 1/4, and then here back to crest. That's a full cycle, right? In the same position with the same velocity. That's a full cycle, or a wavelength when we were talking about waves, right? So for a car, we might have the goal to be for the amplitude of the bump to be gone in 3/4 of a cycle. So then my exponential decay on this would want to look more like this, okay? And then the same thing on the bottom, where it would start up here and go like this, okay? And then that bounds this kind of function where my amplitude of oscillation is basically gone after 3/4 of a cycle, right? And that's the kind of thing you would do if you were designing a car and you were trying to design the ride. You would want to look at your suspension system and say, okay, I want my shock absorbers to have the bounce be gone after a certain amount of movement, right? And then you might say, okay, so I want it to be gone in 3/4 of a cycle. I want it to get bumped here. There's no controlling that. That's just us going over a bump in the road, right? But then when it rebounds, I don't want to have it over damped where it tries to just go down and stop, because then it'll rebound so slow that it won't be ready for like a next bump, right? And so I'm going to let it go all the way down so it keeps some better speed, but I don't want it to bob up and down a lot. So I want it to just go up to down in the trough, and then by the time it gets back to equilibrium, I want to have the amplitude basically gone. So I want to damp it down to 3/4 of a cycle. Okay? So the guy in charge of design might come to the engineers and say, okay, here's who we're going to sell the car to. Here's how these people expect this car to ride. And so here's kind of what I want it to do. And then the engineers are going to say, okay, so what you described is 3/4 of a cycle. And then what we need to do is design the shock absorber so that B constrains the motion to be some percentage gone by 3/4 of a cycle. So let's say that what we want is for, we'll say R equals 0.05. We want the amplitude to be 5% of the original amplitude after 3/4 of a cycle, okay? And that's going to fit what the guy brought to us, the engineers, for how they expected to ride. Right? What he's going to tell you is like, okay, when you go over the bump, I want it to kind of bounce once and then stop, right? That's what he's probably going to say. And then the engineers are going to say, okay, that's 3/4 of a cycle. And what we're going to say is we want the bounce to be down to only 5% of whatever the original bump was by that point, okay? And so if that's the case, phi in this case is going to be 0, right? Because we're always going to start from the top because we go over a big bump. And so the thing starts to oscillate after we go over the big bump. So we're always going to start from the top, which for cosine means that phi is 0. And then what we're really saying is we want omega prime t to equal 3/4 of a cycle, where a cycle is 2 pi radians, right? And so we want omega t to equal 3 times pi over 2, okay? Or you could say 1/4 of a cycle is pi over 2 radians, and we want it to be 3/4 of a cycle, so 3 times pi over 2, okay? And so then A equals RA when omega t equals 3 pi over 2. And that tells us that, therefore, e to the minus b over 2m t equals r. That's just me saying that A equals RA, right? Okay, so the guy in charge of designing the car has brought us, the engineers, certain requirements for the car, and they've allowed us to place these constraints. Omega prime equals this, which is equal to 3 pi over 2, and this e minus e to the minus b over 2mt is equal to r, where r is 5%, okay, 0.05. So then what the engineers are going to say is the thing that makes this happen, the thing that makes it not bob for a long time, is the shock absorbers, right? And so we have to design shock absorbers that have a certain B so that B makes these things happen, right? So what we do is we place these constraints on our values. Omega doesn't equal 3 pi over 2. That doesn't even make sense, right? Omega prime t equals 3 pi over 2. And so we're going to do algebra and just figure out what B must be. So we'll start with this guy. And the first problem is that B is up there in the exponential. So we need to take a natural log to get it out of there. I'm going to get rid of the minus sign as well first. So e to the minus b, if I flip it, it's e to the b over 2m t, and that's going to be 1 over r, okay? Because the minus sign in a power means that it's on the bottom of a fraction. So if I flip it to the top of the fraction, then I have to flip this r to the bottom of the fraction, right? I have to flip the whole equation. So that's that, and then I'm going to have b over 2m times t equals the natural log of 1 over r, okay? And then what I'm going to do is, it seems without motivation now, but you'll pick up on why I'm doing it, okay? When I looked at this problem, I was like, man, this is some crappy algebra involved in this problem. And I sat for a second, and this is the solution that I came up with, which seemed like the easiest way to solve it to me, okay? So I'm going to square the whole thing. B squared over 4m squared t squared equals the natural log of 1 over r, and then that whole thing is squared, okay? And then we go over to the other thing, and we say omega prime t equals 3 pi over 2, right? And then I'm going to square this whole thing, okay? So I'm going to stop writing omega prime. I'm going to write it as omega, okay? Omega squared t squared equals, and then I got to square the other side. So then I have 9 pi squared over 4, okay? And then that means that t squared equals 9 pi squared over 4, 1 over omega squared, okay? And then I take this t squared and I plug it into the t squared over here. So then what we have is b squared over 4m squared. And then if I plug this in for t squared, I get 9 pi squared over 4. And then 1 over, and then omega squared is this thing up here squared, right? So I just get a k over m minus b squared over 4m squared. But then this piece is equivalent. I can rewrite it as 1 over 4m squared over b squared. That would be equivalent, right? When I have a fraction on bottom of a fraction, the bottom part goes to the top. So that's an equivalent way to write this b squared over 4m squared piece, okay? But now you can start to see why I made the choices that I did, okay? Because now that's going to cancel this piece entirely, right? It's just the reciprocal of that. So then this piece equals 9 pi squared over 4, and then 1 over 4mk over b squared minus 1, right? And that whole thing is equal to the natural log of 1 over r squared. Because remember, the whole thing was we were putting in an expression for t squared into this equation right here. So then I want to get the b squared out of the bottom of there. So I'm going to have 4mk over b squared minus 1 is equal to 9 pi squared over 4 ln 1 over r squared. Okay? I'm going to add 1 to both sides. So this is going to become this. Okay? And then to get the b squared out from here, I just take this whole thing and bring it back over to the other side. So then we get b squared equals something where we have 4mk on the top, okay? And on the bottom, we have everything that used to be on the right side of the equation. 9 pi squared over 4. 1 over ln 1 over r squared plus 1. Okay? And so then b equals 4mk over 1 plus this quantity 9 pi squared over 4 ln 1 over r squared. Okay? And that's all in a root. And then with that, the engineers can come back and tell probably another set of engineers, okay, we need to design shock absorbers that have a B of 16,622 kilogram per second. Okay? And that's for all four. So any one of the four would have 1/4 of that. Okay? So when car suspension is designed, in order to make the ride nice, we first have to get springs with a spring constant that gives the system a natural frequency of less than 2 hertz, right? That was the first part of the thing we did here. We have to pick a stiffness of spring that makes the natural frequency of the system not too high, or else the wheel just won't move much when you go over the bump, right? It'll bump the car a lot more. Okay? And then, when we have these springs that are soft enough to keep the frequency below 2 hertz, then we have to design shock absorbers to damp the simple harmonic oscillator that we've created so that it doesn't bounce forever. Okay? So then we calculate this B value that gives like kind of the strength of the damping force, and then we can design a shock absorber that has a strength of damping force that can also be described by this B. And we put that on there, and then we have a nice, comfortable ride for our car. Okay? So let's stop there for today. We'll have one last of these little mini review lectures, and then we'll finish the semester with just one last lecture on material that you won't be tested on, but material that usually people want to hear about, and that's a lecture on relativity.